This is going to be the emulation of PDA problem 7.15 from the Theory of Computation by Wayne Goddard. In problem 7.15, it's asking us to construct a PDA for the language of exercise 6.7. And 6.7 says to us, we're given the CFG 0 to the n, 1 to the n, when n is greater than or equal to 0. So we want the complement. So any other variation of that is what we're going to try and solve. And so we coded this out in Python. The first thing that I did was create a stack. And so now that we have our stack, it's for the PDA, and we're going to look for, if it's an empty string, then we know it doesn't accept it because that's accepted in the original problem. As well, if the problem starts with 1, then we can save ourselves some computing time and not have to worry about anything that's finished after, because we know that that 1 is going to be fine. Then we're going to get into the PDA portion of it, and we're going to append the delta, and then we're going to start going through every single number in the string that is given to us. And from that point, we're going to convert these, each letter. We're going to take them one at a time. We're going to take the letter, turn it into an integer because it's given to us as a string. And they're going to see if it's a 0, then we're going to push an x onto that stack that we have created before. And then we're going to keep track of the position of the string, the index that we're on of the string, so that we know, for example, if it was 0, 0, 1, 1, then we'd know if we were on the third position, we'd be on index 3. We'd be on position 3. Then we would look at, if it's a 1, we can pop an x, so we can just pop, and then we can see if the last one, if the only thing left in the stack is a delta. So if it would be the first. Taking -1 in Python would take the last element. So if the last element is delta, then we know that it can mean only two things. One, if there's an equal number, so if the string is the same length as the number that we popped, then we know it's equal length and it satisfies 6.7, so that means that it can't be correct. However, if it's shorter than that length, so if the string keeps going, it can have more than that many 1s, then we know that it's true. Otherwise, if we read in a 1 and we just pop an x, we can just keep moving along and counting x's and x's and x's. Otherwise, the problem is true. So if we run this real quick, you can see that some examples that we ran that satisfied this 0 to the n, 1 to the n, like 0, 1 and 0, 0, 1, 1, both fail, while ones that don't, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, and 1, 0, 1, all do satisfy what we were looking for.